So, one of the things we want to be able to do is be able to compare. Sometimes you can just compare raw scores or something like that, but you want to know, well, how much better is that? Or is it really better? You know, if you score 3 points per game, are you a good player?
No. It depends on what game you're playing.
If you're playing soccer, you're amazing, right? If you're playing basketball, that's not so good. As you're playing, football.
How'd you do that?
Yeah. So all those things, the context is important to that. Well, okay, so then what if you scored, an average of 0.8 goals per game in soccer, and someone else scores 8 points per game in basketball? How do you compare those two?
Standard deviation.
You can. You use the standard deviation as a ruler. Okay. So here is the idea. So, and we're going to use this. I thought of it because when I took the SAT, I had no idea if my score was good or not. All I knew is here's the score you made, and I was like,
But you get on your SAT.
okay, we'll get to that later in this.
But the scale was different back then.
Yeah, but they still can't find it.
Well, the
Didn't it go up higher?
yeah, it's changed. The scoring is still the same, but where the mean is and what the standard deviation is have changed, and they did that artificially.
How do you do that?
Basically, you change how you count what points they get for getting ones right, and what points they get for getting ones wrong, and all that stuff. It used to be on the SAT that if you answered one wrong, it counted against you.
That's not true.
Yeah, that's no longer true. So that's part of it, but there's been some other things as well. All right, so I looked up the mean scores. Mean score for math that year was 493, and it was 505 for what at the time they called critical reading. Those were the only two sections that they had. Okay? Is that enough information to let me know how well I scored? No, I can say I did better than average or worse than average, but that's about it, right? Okay, well, the question is, well, how much better or how much worse? So here's the idea. To standardize a value, we subtract from the mean and then divide that difference by the standard deviation. This is usually called a z-score. Z-scores, I realized many times I did that and then talked about the word in the next sentence, and everyone knew what it was already. Z-scores measure the distance of a value from the mean in standard deviations. So how many standard deviations above the mean was that? How many standard deviations below the mean was that? And so that allows you to compare two things that are completely different. Because it's standard deviations, you're taking, this has some sort of units, this has the same units. When you divide, this no longer has any units. Okay? So the first thing we do is we shift the data by subtracting the mean. When you add or subtract a constant to every data point, then that adds and subtracts the same constant to the measures of position, but leaves the measures of spread unchanged. So if you, added 10 points to everybody's score, well, that moves up the average score, right? But it doesn't change the standard deviation or the interquartile range or the range. Okay? Second, we change the spread by dividing by the standard deviation. Now, when we multiply or divide all the data values by any constant, all measures of position and measures of spread are multiplied or divided by that same constant. So standardizing into z-scores does not change. Wonder what word I was looking for there. Standardizing z-scores does not change the blank of the distribution.
Range.
Shape.
Yes. Shape is right.
Ew.
But it does change the center. And by making the mean 0, so the average should be 0 then, because you should have some above the mean and some below the mean. And the spread, by making the standard deviation 1.
Z-score big.
So that's our question here. So normal distributions or normal models, excuse me, are appropriate for distributions whose shapes are unimodal and roughly symmetric. So if you connect it at all with a curve, you get that kind of bell-shaped curve that you may have seen before. If not, we'll look at it. A normal model provides a measure of how extreme a z-score is. There's a normal model for every possible combination of mean and standard deviation. This is the way that we're going to write those. The capital N is for normal. Fact is, anytime you write the word normal in this class and you're talking about the normal model, always use a capital N to differentiate it between things that are, ordinary. The mean is this Greek letter. Anyone know that one?
Mu. Wait, we did this in Nancy.
Mu.
I was close.
Yes.
We did that in chemistry.
And a standard deviation, do you know this one?
Yeah.
Omega?
We did it in chemistry.
Oh, darn.
This is a lowercase sigma.
Ew. What is it? I don't like that.
Isn't that what's the E? I thought that was the S.
So I draw it like an almost sideways 6. Okay? So this mean and standard deviation are not statistics based on a sample. They're part of the model and are called the parameters. So statistics is taken from a sample. A parameter is from the entire population. So just remember the S goes with the S and the P goes with the P.
What does that mean? The second part, that a parameter is for the population.
So here, mu and sigma are parameters. They're from the entire population.
Bless you.
That was a laugh. That's the second time
I wasn't sure, so I just didn't say anything.
You did that to her in debate the other day. She laughed and you're like, bless you. Bless you.
Because you like us.
So
No.
if we model data with a normal model and standardize them using the corresponding mu and sigma, we still call the standardized score a z-score, and we write it this way: z is equal to y over mu, y minus mu over sigma. Normally it's easier to standardize the data first, then use the normal model where the mean is 0 and the standard deviation is 1, which is called the standard normal model.
Why do we use Greek letters for math and science and not
Special?
English letters?
It's a really good question, and I'm sure there's an answer for it that I don't know. Okay? It's partly because you start running out of letters to use for things. So, conditions for nearly normal. All right. before trying to use a normal model, you've got to check that the shape of the data's distribution is unimodal and symmetric. If it's not unimodal and symmetric, you can't use the normal model. That's also when you should use the mean and the standard deviation, right? Unimodal and basically symmetric. That was on the quiz, I don't know which one. One of them.
Last one. 3? Yeah. You're like, is that an appropriate distribution of the indicator of the spread? Why not?
Yeah. So check this by using a histogram or the normal probability plot, which is something we'll look at later. Okay, keep in mind that when we use a model, we're making certain assumptions. Whatever model we use, we will always point out those assumptions and the associated conditions in the data to make sure that those assumptions are reasonable. Okay, and I think your book says this multiple times, but all models are wrong, but some of them are useful.
Wait, why are they all wrong?
Because they don't perfectly model what's going on. If you have something in the real world that's happening, it's not going to be perfectly fit to a normal model. Frequently, it'll be extremely close, but not always. All right, so here's a slide that I stole off the internet. The 68, 95, 99.7 rule.
Oh, yes.
Big rule. That's easy to remember.
No.
It's not too bad. So here's what it says is that in a normal model, about 68% of the values fall within one standard deviation of the mean. About 95% fall within two standard deviations of the mean.
Is that how lots of teachers do curves for tests on the bell curve?
This is how, when it used to be, when you would say, is this going to be graded on a curve? They fit the scores to a bell curve.
Can you explain that? Because I've never understood what that means.
So basically what they would do is this. You would take the raw scores of the class. Whatever the mean was for that, you made that, and you could do your bell curve lots of different ways, but mostly they did it as a C. The mean was a C. If you were a standard deviation above, you got a B. If you were 2 standard deviations above, you got an A. If you were 3 or more standard deviations above, you got 100.
So the curve-like number would just be a standard deviation?
The curve-like number.
Like, if I got a 60 and someone added like 10 points.
So the added 10-point stuff, that's not grading on a curve. That's what you think of because that's the way people have done it for ages. They're like, I'm going to curve the grades. No, I'm going to inflate the grades is what they have done. They haven't curved anything. So, and there are lots of ways that you can do that. But when you say grading on a curve, it meant that the median grade got a C.
So it just changes what you define as like an A. Or
Sort of. But it also ensures that if it really is, normally shaped data, then there aren't very many people who are getting an A. If you think about this, if 95% are within 2 standard deviations, that only leaves 2.5% for 2 standard deviations above, right? Half of the 5 that's left over from the 95. So in order to get an A, you had to be in the top 2.5% of people. Okay? And so if this happened, you had a lot of people in the middle, a lot of people making between, and again, it used to be that when you were doing A's, B's, C's, and D's, it was 10 points for everything. So 60 was the lowest passing grade. So there would be a lot of scores then, between 60 and 80. The bulk of your scores would be in there. 68% of them, as a matter of fact, approximately. So if we go back to the SAT, if you were to score 1 standard deviation above the mean, your score is at approximately the 84th percentile. You're like, where do you get 84 from? Well, 50% below the mean plus half of that 68% makes the 84th percentile. You will have to sketch some normal curves. Okay? It doesn't have to be a work of art. You'll see one of mine by hand sooner or later, and you'll be like, okay, yeah, it doesn't have to be a work of art. So what you'll do is, whatever the mean is, and this is for standardized scores, but if it's not standardized, whatever the mean is goes here, and then the mean plus 1 standard deviation goes here, plus 2 standard deviations, plus 3 standard deviations, and on the other side, minus. And you will also mark that 68% of the data falls within 1 standard deviation of the mean, 95% falls within 2 standard deviations of the mean, and 99.7% falls within 3 standard deviations of the mean. Okay? There's a...
What about the 0.3?
The 0.3? Oh, beyond that, there is still a tiny little bit in those, but it's a very, very small fraction. So in theory, the bell curve goes to infinity and to negative infinity, not beyond.
Oh man.
That's kind of a silly statement.
Yeah. Because there is no beyond.
Because there's no beyond.
All right,
So just infinity.
so there are two different ways to find normal percentiles. You can use back to this, when you're sketching this, start in the middle and go out from there. Go left and right from the middle. So pick a high spot and go out. You can stop shortly after 3 because there's just not very much after that. 3 standard deviations to either side. And the curve changes inflection. For those of you in calculus, you'll learn about that soon. But this changes from an overhand motion to an underhand motion right there at 1 standard deviation to either side of the mean. So, it's like an overhand motion on this part, and then it changes to an underhand motion here.
Like a roller coaster.
Pardon?
I said like a roller coaster.
Yes.
Roll a coaster?
Yeah.
Roll coaster?
Roller coaster.
Rollers. Roller coaster.
She's going to name hers that when she owns her own amusement park.
This is my amusement park.
It's the roller coaster.
A roller coaster.
All right. So you can use tables of z-scores, and that'll be given to you on the AP exam. They give you a bunch of stuff. One of them is a table of z-scores. I happen to have some of these here someplace.
You hear the like.
Yeah,
Yes.
we all hear
We
it.
can hear that.
You hear like.
I do want these back because we'll use these occasionally.
See you at the musical practice.
Ian?
I did.
Thank you.
Yes.
Oh, this is my number. Wait, what?
I don't know.
So, if you have a z-score of, say, 0.91,
I don't know what this is telling me.
okay, just hang on. I'm gonna. If you have a z, I know it's confusing. If you have a z-score of, let's just say, let's say 0.91. Okay. Look at the part that looks like this. Right. The one with the big part. Under Z, it says, you can read down there to where it says 0.9, right?
Yeah.
If you want 0.91, you've got to read over to the second column to the right of that, where it says 0.8186.
Wait.
So if you're doing 0.91, right, the column on the left tells you the first decimal place. The columns up, the headings tell you the second decimal place. So if it's 0.91, then 0.8186, that means 81.86% of the scores are less than that.
Okay.
So what's in the body of the table is telling you what percent is less than that. Now, we can do this on a calculator also. And it will be a lot easier. And I'll show you how to in just a second. We're going to use something called the Normalcdf, which is the normal cumulative density function. All right, so let's look at my math score. Okay, the mean score that year was 493. I couldn't find the standard deviation for that, but it's close to 100. So let's find the z-score. So for my particular test, I made a 600 on the math part.
Oh wow.
Oh, yeah. I bet that was pretty score.
No.
600 out of what?
It's just, the scale is exactly the same as is now.
I don't know.
Okay, that's like
It's
what I'm-
800.
That's like what I'm scoring.
So for the z-score for me, that would be 600 minus 493 divided by 100. So that's what, 107 over 100?
Yes. So where is the 100 from?
That's the standard deviation.
That's the standard deviation. So that's 1.07. So you can find that on the table. If you find where it says Table A and continued, yeah, 1.07 if you read across.
So like 80.577.
Yeah, so that means that I was at the 85.77% scored less than that.
Congratulations.
Yeah. And again, I had no idea if it was a good score or not. No
Did
one
you make
ever,
one of these?
no one ever said, you know,
Oh.
well, that and the people that I hung around with were mostly smarter than I was, so I was like, okay,
It's good to hang out with these people.
you know, everyone scored higher than I did. Now, you can also do this on a calculator, and you can do it really quickly. So if you've got your calculator, please grab that.
I have my
Is it charged?
It is charged. It is fully charged.
That's great. I charged my calculator last night.
Sounds exciting.
Inviting.
Hey, what's the other one?
Let's do it then.
All right. So if you go to second vars, which is the distribution,
Second
Second
one.
bars.
vars,
Yeah.
and the second one down is Normalcdf. Don't use the normal PDF.
It doesn't make a
Normalcdf is normal cumulative distribution function.
What is PDF?
I don't remember.
Formative distribution?
I don't remember. So I'll hit enter. Notice it already seeds the lower
That's what mine says.
-1 e to the 99.
Is that
That means
infinite?
-1 times 10 to the 99th power.
very
Wow.
small.
So that's way off to the side. So for my upper, for this,
1 times 10 to the 99999.
no, I want to put in my score,
Okay.
600.
Okay.
600.
New.
Moo.
So the mu,
It's 473. 493.
493,
What is 493 again?
It's a number.
the mean,
Okay.
and the standard deviation,
Is 100.
yeah, we're assuming it's about 100. I can't find the, it's funny, you can find the data on the medians all day long. Nowhere does it tell you what the standard deviation is. And I'm like, well, that's not particularly helpful.
What if your score was lower than 493?
That's
It
an
would be negative.
excellent question. Your z-score would be negative.
Because
You're not on the table.
on here
It goes below 0, correct. Yeah, it actually is on the table. If you flip over to the other side, where is it? Hang on a second.
This is table probability. Mine's
Oh,
table.
that's the wrong one. Hang on. The one that says DF for degrees of, yeah, that's not the right one.
0.857.
How many degrees is that?
That's the one I meant to throw away.
Oh, I can those things.
I can make it massive.
Wait, what's wrong with
I'm gonna
these?
throw mine away.
They're bad. Why are they bad?
3, 2.
I have an
Mine's not
explanation.
really bad. Yeah, it's kind of a hard stuff is no, I'm not throwing mine away.
I should write this speech on this.
Good.
All right.
No, you just, yeah, I do it. Actually, no, I probably
Yeah, you know?
Yeah.
So we put this in, we hit enter.
Oh, I heard that. Oh.
All right, guys. We need to finish this up so we can do your quiz.
Oh, it's already
Oh.
2:40.
No.
Yeah. So notice you get the same thing that we got off of the table.
Yeah.
Did you just press paste?
Did you press
Yes.
paste?
Yeah.
And then you press enter.
What? Oh, okay.
So you could also find all kinds of other things, like what percentage of the people scored between 400 and 500? Okay,
Can you do that?
yeah. You just make the lower 400 to make the upper 500, and it'll tell you what percent scored between those two. So again, go to the distribution, go to the normal CDF.
15.
What percentage of the people scored between 400 and 500?
Oh, 35.17.
And this.
Oh,
Yeah, about 35% of the population scored somewhere between those two.
that's a lot.
That's a lot.
Yeah.
I guess that's where the curve tops out.
Well, the curve tops out at 493.
But like, yeah. Well, it's included in that range, right?
Right.
So
But
I wasn't.
notice
It emphasizes what I'm trying to say.
if we do the normal CDF,
Okay.
what if we did from 393 to 593?
Oh.
What
You're
is,
gonna have 50%.
Do you think so? I disagree.
look at your, it's 68%,
Oh,
Oh.
duh.
right? It should be pretty close to 68%.
That makes sense.
Wow.
About 68% of the data falls within one standard deviation to either side of the mean. Okay.
Word to your mother.
You can also go backwards.
What do you mean backwards?
Well, so what if you wanted to know what score I would have needed to get into the top 10% of the nation? So in other words, 90% scored less than I did. Okay? So again, you can do that backwards on the Z table, which I find difficult. But if you use your calculator, you can use second distribution inverse norm.
So it's the area of 0.9.
Yep.
4.9.
And the mean was 493, and the standard deviation was 100.
And then is it center?
So I would need to have made a 621.
Oh, I
Wait,
dropped. I
Hey,
didn't do it.
what's that saying again? Like, what does that mean? What does that number mean?
That's the score I would have needed
To get in the 90th?
to get into the 90th percentile.
So why is it left? So when would it be like center or
That's so
right?
neat.
I'm sorry?
So when you do it, it asks if you want it the tail left, center, or right.
Does it?
Yes.
Yeah.
On the Z score. Oh, mine doesn't do that.
Mine neither.
Wait, if you do center,
Is
It's
that
a
on
really
inverse
good
norm?
yeah.
If you do left, then it gives you the right answer.
If you do
It's 'cause they have the
center, it
colorful
gives you
calculators.
-1.
We
have the pretty calcs.
Mine
So,
doesn't do that. That's
If you wanted to do, like on this one, to do the top 10%, you could do right and do 0.1.
So if you do center, is it giving you the top 10 and the bottom 10?
It is giving you the middle. So if you did 90%, it gives you, I don't know what it gives you. Does it give you 2 scores?
Yes.
It tells you that 90% scored between the first score and the second score.
328 and 657. But why would it be a different number? Instead of 621, it's 657.
If you do what now?
I did the same thing, but when it's center, the top number isn't 621.
Right, because now your 90% is 45% to either side of 50.
Oh, I see.
So it's gonna be higher.
Okay. That makes sense.
Okay. All right. I think we're gonna quit there.
Quit.
Aw,
I say
can't
stop.
quit.
Quit.
I say stop. You say quit. I say stop.